Okay, so let's go. So we just began work on the parity, introduced the parity operator P yesterday. So what does it do? It makes out of your left hand your right hand if you orient it correctly by producing a state which is the same as the state you first had, but with everything reflected through the origin. So what you used to find the amplitude to be at minus x is now the amplitude to be at x. We showed, not surprisingly, that the square of p is the identity operator, because if you reflect something twice, you have it back where it was, which formally implies that p is p minus 1. And the next item on the agenda is to check that p is a Hermitian operator and therefore an observable. And the proof of that is that we take two states, phi and psi, and we evaluate this complex conjugate. Just make sure that is exactly what I plan to do, yes. So, sorry. Yeah. So we need to do what we want to do, because we know what p does with an x here on the left of p. We slide an identity operator in between the phi and the p. So we write this as d cubed of x, phi x, x p psi. Then we can, and we need to star the whole thing because I decided to star the thing on the left, right? That star is that star. X, of course, is real. Integral sign is real. Then we can use that to replace this. So that becomes d cubed x phi x minus x. Oops, minus x of psi. And then we need to do the starring operation. So that's the integral d cubed x. Take the complex conjugate of that, and it becomes psi, minus x. And then here we're going to have x. And I could write just phi, but just for fun, why don't I write p squared phi, because p squared is the identity operator, so that's safe enough. Except I regard p squared as p times p. And then I can say, look, this p, this outer p, can be got rid of by replacing this by a minus x, because I'm using x, p, some newfangled state phi primed, which is p at phi. So this can be written as the integral d cubed of x psi minus x p. That's this inner p. That outer p has been dealt with by changing that sign on phi. And then I can change my variable of integration from x to x primed, which is minus x. And that's going to produce, is going to be but this, take away the identity operator, sorry, that's x primed, which is minus x. Take away the identity operator, and we're looking at which says that p, since phi and psi are arbitrary, that tells me, comparing with the initial thing, that p dagger is equal to p, which we've also already know is equal to p minus 1. So first of all, this says that it's Hermitian, so it's an observable. And this, p dagger equals minus 1, says it's also at the same time unitary. So it leaves the lengths of all states the same. So since it's Hermitian, so what are its eigenvalues? We have, if p of psi is equal to m of psi, where this is its eigenvalue, or maybe we should call it lambda, more traditional. So if p of psi is equal to m of psi, so it's psi an eigenket, then we can apply p again and get that p squared of psi, which is actually equal to psi because p squared is 1, is also equal to lambda p psi, which is lambda squared psi. So we have that psi is lambda squared psi, and that implies that lambda squared is 1, which implies that lambda must be plus and minus 1. It has two eigenvalues, plus and minus 1. And we say that, so if p psi is equal to psi, we say that psi is an even parity state. Correspondingly, of course, if p psi is minus psi, so if that's an eigenket with the plus 1 eigenvalue, this is an eigenket with the minus 1 eigenvalue, we say it's an odd parity state. What does that mean? From what we have up there, it means that when you, from the top there, the question is, so let's have a look at this. Sorry, let's look at from the wave function point of view, right? For even parity, we can say that x p psi, which is equal to minus x psi by the operation of the p thing, but since p psi is equal to psi, it's also equal to x psi. In other words, the wave function is an even function of x. And similarly, odd parity states have wave functions which are odd functions of x, et cetera, et cetera. And when we did the harmonic oscillator, we found that, for example, n is even parity for n an even number. And correspondingly, it's odd parity for an odd number. Just as a concrete example. So we very often classify our states. It's very useful to know whether our states are even parity or odd parity. We like to work with ones that have well-defined parity. That is to say, are eigenfunctions of this parity operator. By no means all states are eigenfunctions of the parity operator, however. Okay, now we do something considerably more interesting, which is transformations of operators. So we introduced this we introduced the displacement operator, right? Yesterday. So it was called U of A, and it was e to the minus I A dot P over H bar, where P is the momentum operator. And we understood that what it did was it made out of a state, so psi primed being U of A times psi is a new state of the system, the state that it would have if it was identical in all respects, except it was shoved along by the vector A. If you shove your system on by the vector A, the expectation value of the position obviously has to increment by A. Right? So we can make the following statement that the expectation value in the state of psi primed of x has to equal the expectation value in the state of psi plus A, because we have displaced our system. This system is the same as this system, except its location has been incremented, it's been moved by the vector A. And that is logical necessity. But this we can write in a different way. This we can write using that expression as psi times u dagger x u times psi. Right? That's just a rewrite of that using this operator here. And this I can rewrite in a different way, because I can say this vector A, which is just an ordinary boring vector, I could multiply by, well, I could say that this is the following. This is x plus A times the identity operator on psi, right? Because it's clear that the expectation value of A times the identity operator is the vector A. So these are equivalent expressions. So I found that the expectation value of this operator is equal to the expectation value of this operator for any psi whatsoever. And it's shown in a box. It's in the book. It's a little box which leads to the conclusion, the not surprising conclusion, that if that's true, that this expectation is equal to this expectation. If two operators have the same expectation for every state whatsoever, the two operators have to be equal. So this implies, with a little bit of footwork that's relegated to a box in the book, that U dagger xu is equal to x plus a, where this I is perhaps understood. Well, let's put it in, because I want that to be an operator, right? This is an operator on the right-hand side here. Right, now let's now we'll make A small, right? If A is small, we know we can expand this in terms of its generator, right? So we can write this as, this thing here can be written as the identity operator minus I A dot P over H bar plus order of A squared. So we've done that before, and we're going to do it again. So that becomes the identity operator plus I A dot P over H bar plus dot dot dot, which we will ignore, times X bracket 1 minus I A dot P over H bar dot dot dot, and that is equal to X plus A. The I can be understood. So we multiply this all up to find what the terms on the order of A proportional to A are. So A is small but still arbitrary. I mean, you can still fiddle around with it, but it's small. So this is going to give me IXI is going to equal that, right? We're going to get an X on the left-hand side, which will cancel with that. And in the next order, we're going to get A dot P, which is small, because A is small, on X times I, and then we'll have an I times X times minus A dot P. So what we're going to left with in the order of A is I over H bar A dot P comma X. The commutator, because we're going to have this times this, and also with a plus sign, and we're going to have this times this with a minus sign. And what's that equal to? That's equal to A, because that's the terms on the order of A on the right-hand side. The higher order terms must all cancel. That we leave that to the magic of mathematics and not interested in it. So we have this relationship here, and let's look what this looks like in terms of components. If I look at so this is a set of three equations, one for the x component of this, one for the y component of this, and one for the z component of this. So what does it look like? It looks like, let's multiply by I over h bar and swap the order here. Then this is going to be x comma a dot p, commutator, is equal to I h bar a. Now let's write this out in its components. This is, as I say, a set of three equations, so I can say that xj, comma, the sum over k of a, well, it's aj, it's sum over k, ak, pk, but I can take the ak outside the commutator because it's a mere number, is equal to I h bar. I have to write now aj, because this is this component, this vector here matches this here, right? This is a dot product, which is the sum pk ak. And now I can identify. Okay, so this has to be true for all small ak. So I can write this right-hand side as the sum over k if I want to, I h bar, the sum over k of delta j k a k, posh way of writing it. And now I can say, because AK is arbitrary, the coefficient of AK on the right side has to equal the coefficient of AK on the left side. So that leads to the conclusion that xj, comma pk is equal to IH bar delta jk. So we've recovered the canonical commutation relation between x and p as a consequence of p being the operator which generates translations. So we've come at this in rather a roundabout way. Just to review how this has happened. I wrote down a rather arbitrary rule. I introduced p by an arbitrary rule. I said that x p psi is minus IH bar d by dx x psi. Using Ehrenfest's theorem, I tried to persuade you that this wasn't completely crazy. But really, it wasn't a very satisfactory job to start in that way. Then we showed that because P has this d by dx structure, it is the generator of translations. And as a consequence of its being the generator of translations, it must have this commutation rule. And what we should have done, really, is we should have said, look, there must be some operator which generates translations. This operator is going to have this commutation relation, and we should have worked our way down to finding out that in the position representation, it's represented like thus. And for the angular momentum operators, this is the line of argument we're pursuing. We're introducing them as the generators of rotations, and then we're going to find out what they look like in the position rotation and the position representation later on. So we've come at this in a slightly tortuous way. This is the main job that the momentum operator has. It's interesting, so it's probably worthwhile just checking that this commutation relation guarantees that rule up there, that u dagger xu is equal to x plus a, even when a is big, right? So this stuff has all been for an infinitesimal a, and it's good to check that the other thing works, that it sorts us even for a big. So now let's just talk about for any a, including a big one, any big displacement. So we're going to be looking at u dagger, xu. Let me just check my, yep. Which I can write, of course, as u dagger ux plus u dagger x comma u. So I've just swapped the order of those two and put in the commutator that compensates. This, of course, is going to be x, because u dagger u is 1. And what's this going to be? So it's going to be x plus u dagger of x comma e to the I minus I p, a dot p over h bar, close brackets. So this is a classic example. We studied this problem before. We're doing the commutator of x and a function of p. This is the function of p we're doing it. And do you recall that the answer to that problem was that we could write the commutator as the rate of change of this function with respect to p times x comma p. So this can be written as x plus u dagger, the rate of change of this with respect to the derivative of this with respect to p, which is going to be, of course, is going to be u, because the derivative of an exponential is the exponential, times the derivative of what's up here with respect to p. So it's going to be u d by dp of this is minus I. No. let us do this as the derivative with respect to a dot p. Right? We'll regard this as a function of a dot p. I'm worried about components, and the way I can get out of that is considering this to be a function a dot p, which is just one thing. So if I take the derivative of this with respect to a dot p, I get u, because I get the exponential back, and then I have times minus I over h bar, right? That's the derivative of the argument of the exponential with respect to a dot p, and now I have to write down the commutator of x with respect to a dot p. So this, of course, produces 1. And what does this produce? This can be, let's write that down. That's x plus, minus, because of this, I over h bar. This is producing a 1. And now I need the derivative of this, which is the sum over k of x, comma pk times ak, right? Doesn't matter what order I put down a because it's a mere number. And this, it may be that we ought now to introduce an index on x, otherwise we're going to get into a confusion. So let's make that I. So I'm making, this was a vector x, an arbitrary component. Let me call that component I. Then this becomes I. Then this becomes delta IH bar of delta IK. The I and the I make a minus 1, which cancels this. The h bar kills that. So this is equal to xi. And then this is nothing. This is nothing as k is summed, except when k equals I. So that becomes an I. So this just becomes an ai. And yes, it does sort us. That thing is equal to x plus a, as advertised at the top there. So now let's think about rotations. So we introduced these operators. We had jx, jy, and jz, so that alpha dot j generated rotation through mod alpha about the unit vector in the direction of alpha. Right? That's what we established. Well, we used that notation. We said there had to be such a thing. And what we want to do now is talk about, is adapt that argument to this case. So the thing is, the expectation value, let's let psi primed be the state that you get when you use u alpha on psi. So this is the state of the system which is identical to this state, except it's been turned around through an angle around the axis as advertised up there, right? So we can say something about the expectation value of x of this system must be the same as the expectation value of that system, but rotated too. If you've rotated the system, you've rotated the expectation value of x. So we can say that psi primed x psi primed, which is, now this thing is a boring vector, right? It's the expectation value of a vector operator, so it is a boring vector. It's a set of 3 numbers. And a set of 3 numbers we can use a boring rotation matrix on, which I'm going to call R alpha. So this is a 3 by 3 rotation matrix, an ordinary boring rotation matrix, such as I think you must have studied in Professor Essler's course, operating on psi x psi. So this was the old expectation, the expectation value in our unrotated system. If you rotate that expectation value, you must get the expectation value in the rotated system. So that's the analog for the rotational case of that statement, u dagger xu is x plus a. Well, except I haven't yet written what this is, so I'm going to write this as psi u dagger of alpha x u of alpha psi, right? So I'm replacing this with that. And now I'm saying that for any state at psi, this expectation value equals this expectation value. Ergo, since this is a set of boring numbers, it can go inside the expectation and just rotate the operator. So it's just taking a linear, this is a boring 3 by 3 rotation matrix. So if I allow it to go inside there, it's simply going to be taking a linear combination of the x, y, and z position operators. So I'm going to be able to say that u dagger x u is equal to r alpha of x. That's a matrix. And now, of course, I'm going to express this as 1 plus I alpha dot j dot dot dot. So for this is now we're now making small alpha. So we're rotating it through a small angle. Then this can be written thus. Here is our x. Here is our 1 minus I alpha dot j plus dot dot dot. And that is equal to this vector. It's a vector of operators, but still it's a vector rotated by a small angle. Now we know what that is, or at least I hope we do. Come on, come on. Oh no, it's gone to sleep. Do I have to draw? Yeah, sorry, system seems to have. No, it's gone to sleep. So this requires a bit of, this is a piece of just standard geometry. What I want to do is write the action of a rotation matrix for a small angle. If I rotate something through a small angle, and I hate drawing these diagrams, it's going to be something. Has it come alive? Oh, right, yeah, okay. It went to sleep and it needed warming up. So we're looking at this second diagram. Can you see it? Because I enjoy can't. It's too faint. Anyway, so the point is that this is the vector v. Here is the rotation axis alpha. We're rotating through a small angle. Therefore, this distance there is small. The displacement that you have up there, this is the rotated vectors on the right, the unrotated vectors on the left. The displacement is this thing here, which is the vector delta alpha, or the vector. So the small rotation vector crossed with the original v. So that we can say that v prime, the rotated vector, is equal to the original vector plus this small rotation vector crossed into v. So the right side, so I'm not going to draw this horrible diagram. The right side so this is going to become x, that's the v up there, plus alpha cross x. So our R alpha is small, so we don't need the delta alpha. It's just alpha. We made it small to get rid of symbols. So we do the same old stuff. We multiply this out on the left up to order alpha. We notice that the I, the x of the I produces an x, which cancels with the I on the right. And we find that what we're left with to order alpha is alpha dot j times x minus from the I, the x, and the alpha dot j, the thing the other way around. So we find that I alpha dot j comma x is equal to alpha cross x. Now we need to write this in we need to introduce indices in order to disentangle what's going on around here. So this is going to be the sum over k, I times the sum over k of alpha k, which will come out, times jk, all right? That's alpha k jk, comma xj. No, this is, sorry. Let's change that. Let's change that to the thing we sum over to be j. Doesn't matter what we call it, but let's call it that. And call that k, all right? What's that going to be? That is going to be the kth component of this vector on the right. Sorry, we should call that I. Right, this is going to be the ith component of the vector on the right. Now, a cross product can be written as the sum over j and k of epsilon I, j, k. This is the thing which keeps changing its sign. If you swap any two indices, it changes its sign, and epsilon 1, 2, 3 is 1, which I hope you've met in Professor Ressler's course. So this is just writing a cross product in Cartesian tensor notation. Nothing to do with quantum mechanics. It's just standard vector algebra. And we have arranged it so that we have the ith component of the left side here and the ith component on the right side there. Now we play our trick of saying that, look, alpha is arbitrary. It needs to be small, but otherwise it's arbitrary. You can choose its direction any which way you like, and its magnitude in detail you can choose any which way you like. So we can equate the coefficients on the two sides, multiply through both sides by I to get rid of this. You'll get a minus sign, swap the order of these in order to clean it up, and we will have xi, comma, jj is equal to I times, that's this I brought across, the sum over k. The sum over j will go away because we're equating the coefficient of j on the two sides of epsilon I, j, k, xk. This is a terribly important relation. It tells us how j commutes, how the jth component of angular momentum commutes with any component of the position operator. But crucially, in this argument here, we have used nothing about the position operators except that the components form that the x, y, and z operators are the components of a vector. So all of this argument could be repeated for the three component operators of any other vector, for example, for p. So it follows immediately we've only used only property of x used, of the operator x used, is that it's a vector. So we've really shown that for any vector, this relationship holds. So we've shown that vi jj equals I epsilon sum over k of epsilon I, j, k, vk for any vector operator. So a vector operator is just a set of three operators, if you like, whose components whose expectation values will be the components of some classical vector. Okay, so we can immediately apply this as well as to x to vi is pi, the momentum. And we can also apply it to vi is equal to ji, the angular momentum. Why is that?
In the book, you have the j and the v the other way round. Which is right?
Oh, sorry. In which one? This one and this one?
Or in the j is before the x and all the commutations in the book, and the j is before the v.
I lost a sign somewhere. No, I think this is right. Yeah, I multiplied through by I, and I swapped the order of these two, did I?
So is the book wrong?
No, I don't think so. No, but this order is the same as this order, surely to goodness. I don't think.
Yes, but in the book it's the other way around.
Okay, let me take advice on that. I can't help being skeptical, but I suppose I should look here. I suppose I should look. Yeah, true. Yeah, the thing I'm thinking of, okay, so maybe I have, I think have I drifted a sign somewhere? Well, no, this is definitely the ith component of that cross product. This is definitely so. Do we agree about that? That should we just check whether that is whether this ordering is as advertised. This is the closest thing. I can't see it at the moment. I think it's incredibly hard to do these sign problems on blackboards. Let me leave that, and I will confirm tomorrow what the case is. I imagine the book is right and I'm wrong, but I do not see where I have made the mistake as things stand. Everything looks respectable. No, I cannot see an errant sign. Oh, that's nasty. And it does, as you say, matter. Yeah. I'll try and sort that and write up before tomorrow's lecture the way it should be. We need to be persuaded that this, well, the next thing I want to do is be persuaded that this is, so can we apply this to the angular momentum operators? It's going to be very important that we can. And what's the argument? The argument is that alpha dot j has to be a scalar. Why? Because the operator u alpha, which is e to the minus I alpha dot j, this thing is the rotation around a certain vector. What this operator is, this is a physically meaningful thing. And it is defined not by the three numbers that we happen to use to define the direction of the vector, but by exactly what that vector is. If you change your coordinate systems, you use a new coordinate system, you'll be using a new set of three numbers to define this, right? But you must get the same direction in space. And that will be the case if these three operators also transform. So the new operators, the operator associated with Jx primed, where x primed is your new x-axis, will be a linear combination of the old operators, the operators associated with the old axes, using the proper rule for a rotation. Then this dot product will stay the same, and this operator will stay the same as we require. So this operator will be independent of your coordinate system only if these three things transform amongst themselves as for a vector. So J must be a vector, and that means we can use it in here. That is to say, we can say that Ji, comma, Jj, commutator, is equal to I epsilon sum over k, I sum over k, epsilon I, j, k, j, k. So this is a crucial relationship. And from that, we will find out what the eigenvalues can be of these operators, Ji and Jj, and then we'll be able to find what the states of well-defined angular momentum are and everything else. This expression is right, because it's independent of any swap. Can it be that both expressions are right? Oh, I mustn't take time to think about it. Okay, let's consider, what's a scalar? Let's consider scalar operators. So what is a scalar operator? It's an operator which, a scalar in ordinary physics is a number whose value is unaffected by a rotation of your coordinates, right? Like a dot product, it's unaffected by a rotation of the coordinates. So what can we say is that if S is a scalar operator, and then the expectation value of a scalar operator between rotated states must be the same as the expectation value between the unrotated states. Because this is a boring number, and it's evidently, by definition, a scalar. Something's unaffected by rotation, so the fact that you've rotated your system shouldn't have any effect. So when we ask ourselves, so what implications does that have? It's that U dagger SU is equal to S. We can multiply on the left by U, which is the inverse of U dagger, because U is a unitary operator. So we have then that SU is equal to US, which means that S comma U equals naught, where this, of course, is U of alpha, the rotation operator, throughout. So a scalar operator commutes with this rotation operator, and it's easy to see by expanding this as 1 plus. So if we write U is the identity minus I alpha dot J, etc., that immediately goes to the statement that S comma J I equals naught. So scalar operators commute with all the angular momentum operators. There's a very important and interesting scalar operator, and that's J squared, which means the sum over K, JK, JK, aka also known as J dot J, right? That's a scalar operator. Every dot product is a scalar operator, so we have statements like J squared comma Ji is naught. We have statements like X squared comma Ji equals naught. We have statements like P squared comma Ji equals naught. These are all important results that we'll use many times. We have statements like X dot P, that's a scalar operator, comma Ji equals naught, and so on and so forth. So there are many operators we could make out of the operators already on the table which commute with all the angular momentum operators. So just a summary now of the angular momentum commutation relations. We've got that Ji comma Jj is equal to I sum over K epsilon ijk jk. So the individual components, this is a somewhat strange state of affairs, the individual components of angular momentum do not commute with each other. So you can't expect to know simultaneously the angular momentum around the x-axis and the angular momentum around the z-axis. I mean, in individual cases you can, but as a general rule, you can't expect to know that. So there isn't a complete set of states which are simultaneous eigenstates of Jx and Jz, for example. But we do have that J squared comma Ji equals 0, and therefore there is a complete set of mutual eigenstates of the total angular momentum and the angular momentum along any axis. And that's what we have to work with, that we have to consider states which we have to work with states which are mutual eigenstates of J squared, and usually the axis we choose, we have to choose one because of this business, and the axis we usually choose is the z-axis. An important result about parity, let's go back to the parity operator now. So in the same spirit, if I consider, so the expectation value of x, if I reflect my system through the origin, right, by using the parity operator, so I make a system which is like my existing system but reflected through the origin, it's obvious that the reflected system is going to have an expectation value of x, which is minus the original expectation value, right? Because you've reflected everything, and therefore if there was an average value of x in the original system, the reflected system will have minus that value. So this can be written as psi p dagger x p psi, right? Because psi primed is by definition p psi, p dagger here, but we know that p dagger is p, so we have that the expectation value for any state whatsoever of minus x is equal to the expectation value of pxp. So it follows that minus x is equal to pxp. Multiply through by p and use the fact that p squared is equal to 1, and we conclude that px plus xp is nothing very much. So you can say now that that parity, or p, anti-commutes. This condition with a plus sign there, right? With a minus sign, it would be a commutator. With a plus sign, it's anti-commutation, anti-commutes with x, and in fact with any vector, right? Because this argument here really only exploited the fact that we were talking about a vector, not necessarily the position vector. Now, why is this stuff important? The practical importance of this is as follows. Suppose we have a state of well-defined parity. Okay, so let p psi equal either plus or minus psi. Don't care which, but it's going to be, so psi is a state of well-defined parity. And we've seen that the eigenstates of the harmonic oscillator Hamiltonian are actually states of well-defined parity. And now let's consider psi x psi. Well, that we've just seen is equal to minus psi p x p psi. This is a pure rewrite of a line higher up there. Well, except I've taken the dagger off the p, but as we know, p dagger is p, so who cares? So, but we've acquired a minus sign. That's that minus sign. But p on psi is equal to either plus or minus psi. I mean, say plus psi. And p on this psi is equal to plus psi. So these two p's can be got rid of if we put in a couple of plus signs. Or if p psi is minus, we have an extra. We take a minus sign out, but then we get another minus sign from there. So either way, we're taking out 2 of some sign, and therefore this is definitely 1. So we have that it's inevitably the case that this expectation value is equal to minus itself. The only number equal to minus itself is 0. So that implies that the expectation value of x vanishes for all states, all states of well-defined parity. This is a result we use very often, and it doesn't just apply to x, it applies to any vector operator, right? I could have made x any vector operator and repeated the argument. So when you're in a state of well-defined parity, the expectation values of all parity operators are nothing. And I think we've 2 minutes in hand, but I think that is the moment to stop because the next section is on symmetries and conservation laws.